It's time for fun with math, and today we begin our study of trigonometry. And so we begin this question with what is trigonometry? And so basically we can just take a look at the word and dissect it, and it tells us what it is. So of course tri means 3, and a gon, you can think of like a polygon, which is a many-sided figure. So this is sort of a three-sided figure, if you want. So the trigon means a three-sided figure, and then the metri part is sort of the study of measuring. So study of measuring. And if you rearrange these words, basically the last sort of phrase goes first, the study of measuring three-sided figures, or we can just write this as the study of triangles. All right, so it's really just a study of triangles. So that's sort of a literal translation of what the word trigonometry actually means. And today we're going to start with sort of the simple sort of ideas. We want to take a look at angles and some of its applications. So first, let's start with this question. What is an angle? And so it's easy to draw an angle, and you've probably seen these drawn before. So here's an angle right here. Let's make this a 45-degree angle. Right, so there's a 45-degree angle. And if you think about it, what an angle actually is, it's an indirect way to measure distances. And what I mean by this is if you have a figure here, so you suppose you have some let's say some statue here, right? Here's a statue, say it's a person. If you have some sort of statue of a person here, you can use this angle to sort of see what the height might be, versus if you had another statue that was a little bit smaller, so I'll put a person right here. So another person right here is a little bit smaller. You'll notice that to draw the angle, it would be a little bit smaller. So it might be half that angle. So it might be 22.5 degrees instead of the actual here 45 degrees for the other sort of statue. So you can kind of indirectly measure heights or distances by saying, well, clearly the red figure is smaller than the black figure because the angle is smaller. So that's kind of the idea of how you can use angles to solve height type problems, and we'll elaborate on this a little bit more in the future. But let's kind of talk about some things that you already know about angles. And so what do you already understand about angles? In particular, measuring angles, there's actually two ways to measure angles. We can measure in terms of degrees versus radians. So let's just look at an example first, because you usually are well acquainted with degrees. So this is actually we might call the unit circle if you like, but we're going to use it for degrees. And so when you start our degrees on this unit circle, this will always represent right here 0 degrees. And so behind this, I didn't draw this, but behind it, there's sort of an x and y axis. So we can put this on here. So here's the sort of x-axis here. And up here is the y-axis, if I can draw a straight line, which is not easy to do on here, but that's the idea. So there's the y-axis. So right here, we always start 0 degrees right along the x-axis going to the right. And then hopefully you know how many degrees there are in a circle. So how many degrees are in a circle, and hopefully you say there's 360 degrees. So you could reference this angle right here. You could say this angle right here is 0 degrees, or you could wrap all the way around and say it's 360 degrees, and you could go on like that forever. So if you add another 360, you get 720. You could also go the other way, which would be negative. So negative 360 would go clockwise, right? So 360 is counterclockwise, negative 360 is clockwise. So that's 0 degrees, and then all the way around is 360. So we can use sort of the geometry of the circle to try to figure out what the other degrees are. Even though you probably know them, I want you to see how you can build them using this sort of geometry of this circle and basically telling time in a way. All right, so if all the way around is 360, then halfway around right here should be 180 degrees. And then halfway around from 180, which would be up here, should be 90 degrees. And after that, you can count it off. So it goes 0, 90, 180. If you add 90 to 180, you get 270 degrees. And of course, if you add 90, you get back to 360. So that's an easy way to figure out, that this is 90 degrees, 180, and 270 degrees. Now, if it goes from 0 to 90, the angle in between right here is going to be what? It's going to be half of 90, which is 45 degrees. And then we can count these off, right? So that's 45, and 45 is 90. If you add 45 again, you'll get 135 degrees. If you do 45 again, it's 180 degrees, so it checks. If you add 45 again, it'll be 225 degrees. If you add 45 again, you get 270, so it checks. If you add 45 again, you get 315 degrees. And finally, if you add 45 again, you get back to 360, so it checks. All right, great. So now we have a few other important degree markers that we want to find. So we have these angles right here. So this angle and this angle. And you'll notice it splits this first quadrant, right? There are 4 quadrants, really. That's the first quadrant. We call this the second quadrant. We call this the third quadrant. And we call this the fourth quadrant. Right, these are the quadrants. So quad means 4. So quadrants. All right, so this blue angle here and this blue angle here, you'll notice it splits the first quadrant into 3 pieces. There's one piece here, one piece here, and one piece there. And so the idea is if you want to figure out what this angle is, it splits 0 to 90 into 3 pieces. So divide 90 by 3, and that has to be 30 degrees. And so then you add 30 and you get 60 degrees. You add 30, you get 90. Add 30, you get 120 degrees. Add 30, you get 150. So you're just adding 30 each time. So again, I'm just using my ability to add a number each time and kind of tell time in a way. I'm going the opposite way of telling time. Add 30 again, you get 180. Add 30 again, you get 210 degrees. Add 30 again, you get 240 degrees. Add 30 again, you get 270 degrees, which checks. Add 30 again, you get 300 degrees. Add 30 again, you get 330 degrees. Finally, add 30 again, you get back to 360. Everything checks. And now you've filled out all the sort of important degrees that we need to know on this unit circle. In fact, these angles here, the 90, the 60, the 45, the 30, and 0 degrees, these are referred to as reference angles, which we'll talk about in a little bit. So those are called reference angles. Right, they are not, and we'll talk about how to find them on when we're doing when we're drawing angles in a little bit. Now, that was degrees. That's actually the easy one. Now, what's the harder one? The harder one is working with the sort of radians. So let's try to figure out how we do radians. So to do radians, it's basically another way to measure an angle. So for example, you can measure this distance right here. If we measured this, we might find that it's at 1, 2, 3 inches. So 1, 2, 3 inches. But instead of using inches, we could actually figure out what this is going to be in centimeters. Right? So in centimeters, this is going to be equal to, it's about 7.62 centimeters. So 7.62 centimeters. And so you see that a 7.62 and 3 are not the same, but the units matter, right? So 3 inches will be equivalent to 7.62 centimeters. So down here we have degrees, but instead of measuring these sort of angles that we have here in degrees, we can measure in what are called radians. Now you have to have a place to start. So the place that we're going to start is we know there's 360 degrees in a circle, and that's going to be equivalent to 2 pi radians. All right, so we have to remember that in a circle there's 360 degrees, which basically we know, and then we have to memorize that there's 2 pi radians. So down here, what I'm going to write instead of this is 0 radians, and I'm going to write right here 2 pi radians. So that goes all the way around. So what that means now is if you go halfway around, so we go right here, right, that's going to be half. Like it was half of 360 was 180, it's going to be half of 2 pi, and half of 2 pi is just pi. So this angle over here that's 180 degrees is going to be pi radians. And now, to find 90 degrees, what's the equivalent to 90 degrees? Well, you do half of pi, just like you did half of 180 is 90, half of pi is pi over 2. So what I want you to notice here is I'm not memorizing anything but 360 degrees is the same as 2 pi radians. That's all I'm memorizing. Then I'm going to use the geometry of this circle to figure out what the other angles in terms of radians are. So now that I know that's pi over 2, I know it goes 0 radians, pi over 2 radians. If you add another pi over 2, you get a full pi, right? Pi over 2 plus pi over 2 is 2 pi over 2, which is pi. And then if you add another pi over 2, that's going to be 3 pi over 2. So watch, I'm just counting 0, 1 pi over 2, 2 pi over 2, 3 pi over 2. Then I get back to 4 pi over 2. And remember, 4 pi over 2, the 4 and 2 cancel, and you just get 2 pi. So it checks. Now think about how you got 45 degrees here. It went from 0 to 90, so 45 was right in the middle. So you divided 90 by 2 and got 45. We'll do the same thing here. So it goes from 0 to pi over 2. We'll divide that by 2, and that's going to be pi over 4. And now we just count them off. So 0, pi over 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, it checks. 4 pi over 4 is pi. 5 pi over 4s, just counting pi over 4s. 6 pi over 4, which that checks because it reduces to 3 pi over 2. So from 6 pi over 4, we go to 7 pi over 4. That's this angle here. And you got another pi over 4, and you get 8 pi over 4, which notice that checks because 8 pi over 4 is 2 pi. All right, now we want to write off the last angles that we have here. So remember how we got this 30 degrees here, really. You notice that this angle here splits it into first quadrant into 3 pieces. So 1, 2, 3. So to find this angle, you just did 90 divided by 3. So it's the same thing here. Pi over 2, we're going to divide that by 3. So think about it. If you take pi over 2 and you divide it by 3, remember that's like 3 over 1. What is that going to be equal to? It's just pi over 2 times 1/3, which is pi over 6. So this angle right here in radians is pi over 6 radians. So that's 1 pi over 6. That means this is 2 pi over 6. And we'll reduce that later when we come back to it. Then we get 3 pi over 6, which is pi over 2. This will be 4 pi over 6. This will be 5 pi over 6. This is 6 pi over 6, so it checks, that's pi. Then 7 pi over 6. 8 pi over 6, which of course will reduce, but we'll come back and reduce it in a minute. 9 pi over 6, which checks, that's 3 pi over 2. 10 pi over 6. And then 11 pi over 6. And then finally 12 pi over 6. I'm just counting. So 12 pi over 6, which you can see if you have 12 pi over 6, the 6 goes into 12 twice, so you just get 2 pi. And so it just goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pi over 6s. We should go back and we should reduce probably, so the 2's cancel, so it's really pi over 3 radians. This is really 2 pi over 3 radians. This is really down here 4 pi over 3 radians. And this one is equal to 5 pi over 3 radians. So this is labeling the angles in terms of degrees and radians on what we say is the unit circle. So sometimes students ask me the question, do you have to memorize the unit circle? And I say yes and no. You don't really have to memorize it, but you do have to remember that there are 360 degrees in a circle and 2 pi radians is equivalent to 360 degrees. And if you know that, it's easy to recreate all the angles on this unit circle. And remember, these angles here, just like before, the 90, the 60, the 45, the 30, and the 0 radians, these are actually referred to as reference angles, which we're going to talk about in a little bit. Sometimes I tell you guys in this section, note cards are key because you can write on the front of a note card like 30 degrees, and on the back of the note card, when you flip it over, you can write pi over 6. And you want to basically equate pi over 6 radians with 30 degrees, pi over 4 radians with 45, pi over 3 with 60 degrees, and pi over 2 with 90 degrees. And then after that, you can remember all these if you know all those. That's the sort of idea with reference angles. Like if you know the reference angles, you can kind of understand all the other angles in terms of them. Okay. So what's next? We want to talk a little bit about drawing angles in standard position, reference angles, and the quadrants, which we've sort of already mentioned. So let's just look at some examples here. So we want to look at this angle, 120 degrees. So to draw that angle, I'm going to draw this sort of x and y axis here. So here's the x and here's the y. And to draw 120 degrees in standard position, so what standard position means is you always start the angle along the x-axis. So there's my start of my angle. And then I'm going to go 120 degrees. So the idea is you go over 90, and then you're going to go, what, 30 more? So right here, this is, let's do it right here. So this is about 120. The angle right here is 120 degrees. And standard position, again, means start along the positive x-axis. So to figure out what quadrant, and find its reference angle. So the reference angle is always the smallest angle it makes with the x-axis. So there's basically two angles here. You have 120 with the x-axis, or you have this angle here, which is 60 degrees, because remember to go all the way around to 180. And so that's the reference angle. It's the smallest angle it makes with the x-axis. What's the reference angle? Right, so here we can write this down. So reference angle, right? This is the smallest angle it makes with the x-axis. And then what quadrant is it in? Now, how many quadrants do you have? So remember, you have 4 quadrants. You can label them. There's quadrant 1, there's quadrant 2, there's quadrant 3, and there's quadrant 4. And so this lies in quadrant 2. And so we did all 3 parts. We drew the angle in standard position. We found its reference angle. And we said it's in quadrant 2. So now let's do this again. But this time, let's do it for negative 330 degrees. So over here, I'll redraw my x and y axis. I want to draw my angle now. So negative 330 degrees in standard position. You're always going to start. Standard position means you start on the x-axis like this. And then the negative sign means instead of going counterclockwise, you're actually going to go clockwise. So you're going to go this way. So the idea is you go basically negative 90, negative 180, negative 270, and then 60 more. So you're right here, basically. And so then we draw this like this. And so that's negative 330 degrees. We can draw the reference angle. Again, it's the smallest angle it makes with the x-axis. So it's right here. So it's negative 330. So to get down here, you just go an extra 30 degrees. That'll give you the 360. So the reference angle is 30. And then finally, which quadrant is it in? Well, we'll just list the quadrants and we'll circle the one it's in. So there's quadrant 1, quadrant 2, quadrant 3, and finally quadrant 4, and it's in quadrant 1. And so that's how we draw angles when they're in degrees. Now, how do you draw angles when they're in radians? Right? So now remember, when you see these radians, you have to remember some stuff. You have to remember when you see pi over 3, that really is equivalent to 60 degrees. And pi over 4, that's equivalent to 45 degrees. And when you see pi over 6, that's equivalent to 30 degrees. And then, pi over 2 here, I didn't write this one down, I guess it's over here. Pi over 2 is equivalent to 90 degrees. And of course, 0 degrees is equivalent to 0. Oh, I guess what I was doing on the left. So 0 radians, so 0, right, rad for radians, is the same as 0, is equivalent to 0 degrees. So let's look at this. Again, we want to draw this angle in standard position. We want to find its reference angle. We want to figure out which quadrant it is in. So down here, let's draw our xy axis. So here's my x-axis. Here's my y-axis. We'll draw this in standard position. So if I see 5 pi over 4, what that is 5 pi over 4s. So we'll start in standard position, so start here. And you can do pi over 4 5 times, or basically 45 5 times. So it's like, here's 1 pi over 4, here's 2 pi over 4, 3 pi over 4, 4 pi over 4, and 5 pi over 4. So right down here, sort of halfway in between, this is the angle 5 pi over 4. And now we want to find the reference angle, so I can draw the reference angle. It's right here. It's just the smallest angle it makes with the x-axis. And if you think about how you counted it off, this was 4 pi over 4, and you went 1 more pi over 4 to get 5 pi over 4. So this is just pi over 4. The rule of thumb is if it's given to you in radians, your reference angle should be given in radians. If it's given to you in degrees, your reference angle should be given to you in degrees. And to figure out which quadrant it's in, you could probably just look at it and tell me it's in the third quadrant, but we'll write them down. Here's 1, 2, here's the third quadrant, and that's what we're in. And of course, there's a fourth quadrant, but we're in the third. All right, let's do 13 pi over 6. So again, let's draw the x and y axis. So here's the x-axis, here's the y-axis. And we want to draw our angle. And so it's 13 pi over 6, so I know where to start. You always start in standard position. You always start here on the x-axis. 13 pi over 6 is 13 pi over 6s, or if you want, it's 1330 degrees. So basically you get 3 in the first quadrant. So it's like pi over 6, pi over 6, pi over 6, there's 3. Pi over 6, pi over 6, pi over 6, there's 6 of them. Pi over 6, pi over 6, pi over 6, there's 9 of them. Pi over 6, pi over 6, pi over 6, there's 12 of them. And one more pi over 6 puts us right here. And so when we draw this angle, we wrapped around all the way once and came up an extra pi over 6 right there. So that's 13 pi over 6. It's important to draw this little sort of angle, this sort of little swirl that tells you go around more than once. So that's 13 pi over 6, and you have a little arrow on the end. I don't know if you've noticed that, but there's a little arrow on the end there. To find the reference angle, we have to think about how we counted that off. So we got to 12 pi over 6, and we went one more. So to get 13 pi over 6, that's actually pi divided by 6. That's the reference angle, the smallest angle it makes with the x-axis. There is another angle it makes with the x-axis, which is all over here, but it's bigger. So we always take the smallest one. And then which quadrant is it in? Well, we can list the quadrants. You have 1, 2, 3, and 4, and clearly the angle right here is in the first quadrant. It's where this sort of terminal end, we sometimes call this the terminal ray. It's where that terminal ray ends. That's the quadrant of the angle. Okay, so let's move on. So we talked about what an angle is. It's sort of an indirect way to measure distances, in a sense. Trying to understand angles. What have we done? We've talked about degrees versus radians on a unit circle. And we drew some angles using standard position, talking a little about reference angles and quadrants. And we want to finish up with some applications. So, of course, there are two ways to measure angles, degrees and radians. We would like to be able to convert between the two. Sort of like just like we would like to be able to go between inches and centimeters, we would like to be able to go between degrees and radians. And to do that, we use something called conversion factors. So what's a conversion factor? Well, let me give you an example we've kind of already used. Suppose you have 3 inches, and you want to convert those inches into centimeters. So how would you do that? So this is some of a physics or chemistry problem. So the idea is you would multiply by what's called a conversion factor. And so on bottom, you would have inches, and on top, you have centimeters, and this would be the conversion between inches and centimeters. So in 1 inch, we have 2.54 centimeters. So up here, we'd write 2.54 centimeters. We would do this multiplication, and if we did this multiplication, we would get 7.62 centimeters. So we actually know that 3 inches, if you want, so 3 inches is equivalent to 7.62 centimeters. We can do a similar thing to figure out how to turn degrees into radians. So we're going to multiply by a conversion factor. All right, so over here, this is called the conversion factor. So our conversion factor will have degrees on bottom and radians on top. And we just have to figure out how many degrees here are there with relationship with certain numbers of radians. Now, I told you we're going to memorize here that 360 degrees is the same as 2 pi radians. So you can use this as your conversion factor. But if you think about it, what this actually means is that 180 degrees is also the same as pi radians if you divide both sides by 2. So we normally use these two numbers because they always simplify up here. So down here we usually put 180 degrees, And then above it, that's equivalent to pi radians, and so that's the conversion factor. It's going to turn degrees into radians. And it's easy to see why. You can see the units. Degrees here are going to cancel, and it's going to leave you with radians in the end. Just like here, the inches cancel, and it leaves you with centimeters in the end. And so to do this, we may need to do a little bit of simplification here, so simplifying. So notice that 105 is actually 5 times 21. That's 5 times 21. And then 180 is actually 5 times what? So 20 is 100 and 16 is 80. So that must be, what, 36? So the 5s are going to cancel. And it's going to leave us with 21 pi divided by 36. And we can keep on simplifying here. So it's, 21 is, what, 3 times 7? And 36 is 3 times 12. And this is a good sort of process to go through so you can work on your simplification, your basic arithmetic. So you're going to have 7 pi divided by 12 radians left over. And you can check that with your calculator if you want. But remember, we're supposed to do most of these calculations by hand. So that's probably the best way to do it. So you get 7 pi over 12 radians. Let's do this again, but now let's use negative 480 degrees. So we're going to use a conversion factor. And so the idea is we're going to go from degrees to radians. And I know that in 180 degrees, there's actually pi radians. And so we do the same thing again. Now this time it's a little bit easier to simplify because these are both multiples of 10. So let's do that. So let's say that's 48 times 10, and that's 18 times 10. So the 10s will cancel. And on top, I'm going to be left with negative 48 pi divided by 18 on the bottom. All right, remember the degrees here and here are going to cancel. And so that's going to be equal to, now there are a couple ways to do this. I can look at negative 48, and the first thing I'm like, oh, that's 6 and 8, so that's 6 times 8. And then down here, this is 6 times 3, so 6's are going to cancel, and I'm going to be left with negative 8 pi on top and a little 3 on the bottom. And that's radians, so we should put the radians on there. Although if nothing's written, it'll be assumed that it is in radians, but we should practice writing radians. And so that's how we convert from degrees to radians. All right, now, once we can go one way from degrees to radians, of course, we'd like to be able to go back. So in the next example, we want to convert now from radians to degrees. And it's just as simple. The only difference is instead of having degrees on the bottom, we're now going to have radians because we want the radians to cancel. And now we'll have degrees on top. And so again, in 180 degrees, there's pi radians. So basically the same thing. When you do this multiplication, notice you have a pi on top and a pi on bottom, so they're going to cancel. This on top and bottom, they're going to cancel a little bit, at least a little bit. So when I look at this, remember 4 is 2 times 2, and this is 2 times 90. So that's my first idea. So the 2's will cancel. And so what I'm going to get here then is 7 times 90 divided by 2. And now here, the 90 and the 2, you can divide that out, and that's going to be 7 times 45. And then to do this multiplication really quickly, remember 7 times 45 is like 2 45s, 2 45s, 2 45s, and an extra 45. So my brain's like it's 90, 90, which is 180, plus another 90, which is 270, plus an extra 45, which is, what, 315? So 315 degrees. And you can check it with your calculator, but make sure you can do the basic arithmetic in your head, right? Sort of quickly, right? That way your brain, when it makes these computations, it can do it quicker than the calculator, really, and you don't your eyes never actually leave the screen. Right? Remember, once your eyes leave whatever you're looking at, your brain sort of forgets about everything that's going on here. It loses track of it. If your eyes can stay in one place while it's solving the problem, your brain will track it subconsciously. You're not aware of this, but it'll track it. So it's best to do these basic calculations while you're looking at it. All right, let's try this one now. So now this one, again, you want to go from radians to degrees. So on bottom, we have radians. And on top, we have degrees. And so in pi radians, there's 180 degrees. And we can simplify this. So we're going to multiply this out. And so what's going to happen is the pi's, again, are going to cancel. You have a pi on top and a pi on bottom. And so are the radians. So if you want, you can cancel out the radians. Now 6 goes into 180 nicely, because remember, 180 is actually 6 times 30. So the 6's are going to cancel. And so what you get here is negative 11 times 30 Now this one's kind of an interesting one. It's hard to kind of do this in your head at first if you don't think about it right. But remember, 11 is really a 10 and a 1. So it's like 10 30s, which is 300, plus an extra 30, which is 330s, so you get negative 330 degrees. Right, so if you think about this problem correctly, like 11 times 30, it's like 10 30s and 130. Well, 10 30s is 300, 130 is 30, so it's negative 330 because there's a negative sign there, and that's your answer. And again, you can check it with your calculator, but you need to make sure you can do this by hand. All right, so finally, we're going to talk a little bit about what are called angular models, so using angles or angular ideas to model things. So let's look at our first question. And of course, it's probably one of the most popular angular models, which is the clock. So it says the minute hand of a clock moves around from 12 to 5 o'clock. How many radians did the minute hand move through? So let's just draw a picture so everybody can, see what's happening here. So here's my clock. If you want to label the clock, it goes 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, back to 12, right? So you can label it if you like. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what happens is it says the minute hand, we'll just put the minute hand right here, moves from 12 right here down to 5 right there. And it passes through some angle, clearly. And we want to find what that angle actually is. So we can label this if you want. If you want to call it, sometimes we'll call angles theta. And so here, to figure out what the angle is in radians, so how do we figure that out? Well, you can write down the angle theta. And one thing you can do is you can say, well, there's 12 ticks on this clock. So what has happened is it's gone through 5 of those ticks. So basically, it's made 5 over 12, 5/12ths of a revolution. All right, so you can write down that. That's not in radians, that's in terms of revolution. So it's 5/12ths of a revolution. But you can turn a revolution into radians pretty quickly. Right? So what can you do? You can think about this. We want to go from revolutions to radians. And so 1 revolution is a full circle. How many radians are in a full circle? 2 pi. So we can extend this idea of conversion factors, because again, they work for almost everything, right? Conversion factors are the way we change money, right? If you change $1 into dimes, $1 is equivalent to 10 dimes. Or if you even change currencies, right? So you can change dollars into pesos or euros or yen or whatever using conversion factors. And so you see here what's going to happen. 12 is 6 times 2. So the 2's are going to cancel. And so on top, you're going to get 5 times pi, which is 5 pi. And on bottom, you're going to get a 6. The revolutions cancel, and you're left with the radians. So you have 5 pi over 6 radians for our answer. Now, it wants to ask the question, if the minute hand is 9 inches long, then how far did it travel? All right, so now that's a little slightly different question. So this is 9 inches long, and then when it travels, it goes through this sort of arc right here. It wants to find what that distance actually is, right? So what is that distance d that it travels? Now this one's really interesting. So right now, I know it's 5 pi over 6 radians. We haven't talked about this yet, but the word radians has a meaning. So if you look at the word radian, what word does it remind you of when you talk about a circle? And hopefully, when you see radian, you think, this reminds me of radius. And that's basically the idea. Every circle has a radius, and if you measure off a single radian, right, a single radian here, so if you measure off a single radian, right, if this is 1 radian, so if that angle right there, I'm going to write over here, is 1 radian, 1 radian. Do you know what this green distance is? This green distance here will be 1 radius. That's the actual definition, in a sense, of a radian. which is really nice. It's like, hey, if you have a radian, it means 1 radius. So right here, I want to go from radians. Right, I want to go from radians into a distance which is inches. But I know in 1 radian, remember 1 radian is 1 radius, and what's the radius? It's 9 inches. So that's the conversion factor to go from radians here into inches. Right, so 1 radian is 1 radius, and the radius is 9 inches on that circle. So this is going to be equal to, and of course you get some cancellation, that's 2 times 3. That's 3 times 3. And so this is going to cancel with that. And so I get 5 times 3, which is 15. And you have pi, and you're going to divide out by the 2. And so you have 15 pi over 2. And notice the radians canceled, so what you're left with is inches. So you get 15 pi over 2 inches. So, all right, so another example using sort of angular models. Here it says the angular speed of a wheel with a radius of 15 inches is 20 revolutions per minute. So let's try to understand what this is saying. So you have basically a wheel. So here's my wheel. So this is my picture. And it has a radius of 15 inches. So we'll draw a radius on here of 15 inches. And it says a revolution of 20 revolutions per minute. So basically this thing is spinning around. I don't know which direction, but it doesn't really matter. So it's spinning around that way at 20 revs per means to divide. So 20 revs per minute. We want to determine the angular speed in terms of radians per minute. All right, so the idea is you know the angular speed in terms of revolutions per minute. So this is revs per minute. And then we're going to use a conversion factor to convert revolutions into radians. So we're going to multiply this by, and we want to get rid of revolutions, so we'll put that on the bottom. And we want to wind up with radians, so we'll put radians on top. And so we have to ask ourselves, how do we convert from revolutions to radians? Well, in 1 revolution, there's 2 pi radians. So if you go around the circle 1 whole time, you went the same as going 2 pi radians. And so then we see here, if you multiply 20 by 2 pi, you get 40 pi. The revolutions are going to cancel. And then you have radians on top. So radians. And then on the bottom, per, you have minutes left over. So you get 40 pi radians per minute. And so that's the angular speed in terms of radians per minute. And then, of course, you want to determine the linear speed of the wheel. So if the wheel is turning and you set it on the ground, it's going to start taking off. In this case, it'll take off in this direction. How fast will it go in that direction? So to find the linear speed, the idea is you take the angular speed and turn it into it. And it's really not that hard to do if you think about it. So you have 40 pi radians per minute. And again, you want to change this radians, right? So now linear speed, so you have to kind of know where you're going. So remember, linear speed in this case will be inches per minute. So I know I need to turn this into inches per minute. It doesn't say that, so you have to figure that out from the problem. So because you know what linear speed is, right? Linear speed is like in miles per hour, but in this case you have inches and you're in minutes, so it's inches per minute. So the idea is minutes can stay, but radians has to turn into inches. So you get rid of radians, and then you put inches on top. And then you got to think about what that conversion factor actually is. And remember, radius actually means radian actually means radius. So remember this. That's why it's called a radian. It actually means, in some sense, radius. So if you have 1 radian, that's 1 radius, and 1 radius, remember, is 15 inches. So in 1 radian, there's 15 inches. And so then we do this multiplication, 40 times 15, which is really 40 and 10, which is 400, and then 5 times 40, which is 200. So you're going to get 600 and then pi inches per minute. And that's the linear speed. So, real quick, to kind of review, So what is an angle? So remember, an angle is really sort of an indirect way to measure distances in a sense. Understanding angles, remember there's two ways to measure angles, in degrees and radians. This is sort of similar to the idea there's two ways to measure distance, in the sense there's centimeters and inches, or if you want miles and kilometers. You can draw angles in what we call standard position, find the reference angle, which is the smallest angle it makes with the x-axis, and of course there's four quadrants, so you can say what quadrant is in. And then there's some applications, and the key to the applications, remember, is this conversion factors, right? We use this a lot in chemistry and physics to convert between units. And we also use it in applications of angles to sort of solve these angular modeling problems.